Welcome to today's webinar. The webinar is organized by the New Zealand Stainless Steel Development Association, the University of Canterbury in Christchurch, supported by the Steel Construction Institute and conducted by the International Molybdenum Association and the Nickel Institute. It covers the topic State of the Art in Stainless Steel Structural Research. Today's presenters are Ms. Nancy Badu, Associate Director at the Steel Construction Institute, and Dr. Francisco Meza, Principal Engineer at the Steel Construction Institute. Our panelists of today are Dr. Ke Tsiang, Lecturer in Structural Engineering at the University of Canterbury in Christchurch, and Paul Geppert, Executive Director of the New Zealand Stainless Steel Development Association. I'm your host today, Jörg Schweitzer, Manager Market Development in Southeast Asia. With this, I would like to wish you all a very interesting webinar, and over to you, Nancy and Francisco.
Okay, so hello everyone, and welcome to this last webinar. Here you have the outline of what we're going to cover today. I'm going to start by giving you an introduction to the continuous strength method, which is a new design method for calculating the cross-sectional resistance of stainless steel members. And then I'm going to tell you about the situation with the seismic design of stainless steel structures. And after that, I'm going to hand over to Nancy, who will talk about the design of stainless steel composite members and slip-resistant connections. To complete the webinar, Nancy will also tell you a little bit about the research on stainless steel, which is currently underway. Okay, so we will start with the continuous strength method. This is basically a new design method that can be used to calculate the cross-sectional resistance of stainless steel members. The method is included in the American stainless steel specification, which is C370, and it will also be included in the next version of the stainless steel Eurocode. The method is different from any of the methods you might be familiar with. And the key of this method is that it is able to take into account the additional strength that result from strength hardening. Now, one important thing about this method is that when you use this method, you need to be aware that it is only applicable for members that are not susceptible to global buckling. So for columns, that means that the resistance is not governed by flexural buckling, torsional buckling, or flexural torsional buckling. And for beams, the strength is not reduced due to lateral torsional buckling. So this implies that your columns or beams will have to have a sufficient amount of bracing to prevent the global instabilities. The continuous strength method is particularly beneficial when designing non-slender or compact cross-sections, because in this case, the resistance predicted by the CSM will be larger than the yield load, which is obtained by multiplying the gross cross-sectional area of the column by the yield strength. And in the case of beams, it will be larger than it might be larger than the plastic moment capacity. Now, the continuous strength method can also be used when the strength of the member is governed by local buckling. But in this case, the resistance you will get when using the CSM is not going to be significantly larger than the one you would get when using the traditional method. Okay, so with the traditional design method, which was originally developed for carbon steel sections, if we want to calculate the resistance of the of a cross-section, we first have to check the susceptibility of the cross-section to local buckling. And we do this by looking at the width to thickness ratio of the most slender element of the cross-section. If the cross-section is slender, that means that local buckling occurs before the cross-section is able to reach the yield load. And in this case, the effect of local buckling is considered by using the effective cross-sectional area or an effective section modulus. As for the stresses, this method assumes that the effective cross-section is going to be able to yield. And because of this, you always use the yield strength when calculating the resistance. Now, if the cross-section is non-slender or compact, that means that that failure will be governed by yielding of the cross-section, and which will happen before local buckling takes place. And in this case, the cross-sectional resistance is calculated by multiplying the yield strength by the gross cross-sectional area of the section modulus. Now, because of this, any additional strength that results or that could result from strength hardening is ignored. So for sections that are made of carbon steel, this design approach might offer a good approximation because the strength hardening of carbon steel is not that significant. But for stainless steel, this assumption might be too conservative, especially for austenitic stainless steels, which are the ones that have the largest strength hardening. So with the continuous strength method, you don't need to check whether the cross-section is slender or compact. All cross-sections are treated exactly in the same way. So the principle that is behind the CSM is based on the idea that if we ignore global buckling, any structural shape under compressive stresses will fail due to local buckling. So the first thing you have to do when using the CSM is calculate the maximum strain the cross-section can resist before failing due to local buckling. To do this, you have to calculate the slenderness of the cross-section, and then you use the base curves that you can see in this slide to calculate the maximum strain the cross-section can resist. Now, these curves you can see here are presented as equations in the stainless steel design codes, and they were derived based on tests on beams and columns with different cross-sectional slenderness. So once you have calculated the maximum strain the cross-section can resist, you can convert the strain into stress by using the CSM bilinear stress-strain material model, which is the one you can see in this slide. Now, you might have noticed that there are a few coefficients that are used to define the material model. And this is because this material model is slightly different for each stainless steel alloy family. For example, for austenitic stainless steel, the slope that defines the strength hardening is steeper than for duplex stainless steel. Now, once you have once you know the stress distribution within the cross-section, you can calculate the cross-sectional resistance. But instead of you having to derive these equations, this resistance equation, the stainless steel design code will give you the equations that you need depending on whether the cross-section is subject to compression, bending, or any other type of loading. Now, you can see from this figure that if the maximum strain the cross-section can resist is lower than epsilon sub y, then the maximum stress the cross-section, the maximum stress in the cross-section is going to be lower than the yield stress. And this would be effectively the case of a slender cross-section. And in this case, you will not be able to take advantage of the strength hardening. Now, if the maximum strain the cross-section can resist is larger than epsilon sub y, that means that the cross-section is either non-slender or compact, And in this case, the cross-sectional resistance you will get using the CSM is going to be larger than you would get if you use the traditional design method. Okay, well, so you can use the continuous strength method using the nominal yield strength of the material. Or as I mentioned during the second webinar, for cold roll and cold form section, you can use the increased yield strength due to cold working. So in this table, I'm comparing the cross-sectional resistance you would get for cold roll structural hollow section columns when using the CSM and when using the traditional method. For the case in which you're using the CSM, the resistance I'm showing here in this table were calculated using both the increased yield strength and the nominal yield strength. So just so you are aware, all the cross-sectional dimensions that are shown in this table are given in inches. And if you look at the table carefully, you will see that you don't always achieve a larger resistance when using the CSM compared to the traditional method. The increase in resistance is only achieved for cross-section that are compact. So this type of cross-section can develop strength hardening. So you can see that if you use the continuous strength method using the nominal yield strength, so in this case, you should be looking at the last two columns of the table, you can get an increase in compressive strength of up to 25% for the most compact cross-section. And as you combine the CSM with the increased yield strength, so in this case, you will be looking at the second and third column. In this case, you might achieve an increase in strength of around 50%, and in some cases, even higher. So one thing you might have noticed as well is that the largest increase in resistance is for austenitic stainless steel, which is the stainless steel alloy that benefit the most from the continuous strength method. Okay, well, now I'm going to tell you about the situation with the seismic design rules for stainless steel structures. So at the moment, the seismic design of stainless steel structure is only covered by the Japanese and the Chinese standards. And in this design codes, the rules for stainless steel structures are essentially the same as the one that are given for carbon steel. The Eurocode doesn't cover the seismic design of stainless steel structures. And the reason for this is because most European countries are not located in seismic regions. And because of this, there hasn't been an initiative to extend the carbon steel rules to stainless steel structures. In the US, the seismic design only mentions cold form stainless steel structures, but design rules for this type of structures are not comprehensive. So as you might know, the US is affected by earthquakes more than Europe. So the reason the American Seismic Design Code does not cover stainless steel structures other than the cold form structures is because design rules for stainless steel have only recently been introduced to the US with the development of AIC 370 in 2021. Now, very recently, there has been an initiative in the US to see if it is possible to give at least some simple rules for stainless steel structures and also identify what is needed to develop more comprehensive seismic rules. So as part of this initiative, the Steel Construction Institute, we have written a Part 3 resort paper for the NEHRP, which stands for National Earthquake Hazards reduction program. So in this paper, we have looked at the state of the art in terms of the research that had been carried out on the seismic performance of stainless steel structures. We have recommended ways in which some of the rules for carbon steel could be extended to cover stainless steel. And we have identified the research that is needed in order to develop more comprehensive and efficient rules for stainless steel. The paper we wrote is currently under ballot, and any possible incorporation of the recommendations that are given in the paper into the American Design Codes is still a few years away. Now, the relevant American Design Codes are ASCE 7, which gives provision for how to calculate the seismic forces that are applied to the structures, and also gives reference to the relevant design code that you have to use when designing the structure. There is also AISC 341, which is the code that gives specific provisions for the detailing and design of steel structures that are subject to seismic load. So you might be wondering if the Japanese and the Chinese seismic design codes say that the rules for carbon steel should apply to stainless steel, why we don't say the same thing for the American code? So one of the reasons is that the Japanese and the Chinese seismic codes are more conservative than the American code. And because of this, if we want to extend the carbon steel rules in the American code to cover stainless steel, we need to, this would be something that needs to be discussed, and it has to be think carefully. So in the next few slides, I'm going to explain very briefly some of the content of this paper we wrote. Okay, so as I mentioned during the second webinar, stainless steel is at least as ductile as carbon steel. And as you know, this property is very important because during an earthquake, the energy that is induced by the earthquake is required to be dissipated through inelastic deformation of some key structural elements. So in this regard, austenitic and duplex stainless steel should have no issue meeting the ductility requirements which are given in the seismic codes. Austenitic and duplex stainless steel also have similar or superior toughness to carbon steel, which is important to avoid brittle type of failure modes. Another important characteristic is weldability. And both austenitic and duplex stainless steel have good weldability. And this means that their welded joints can achieve good strength, ductility, and also good toughness. Now, you need to be aware that duplex stainless steel might require preheating before welding. And also, they don't have a pre-qualified welding procedure in the American welding standard. And that means that if you need to weld duplex stainless steel, you will need to develop your own welding procedure. So here I'm showing you the hysteretic behavior of a typical carbon steel grade that is used in structures that are subject to seismic loads, and the hysteretic behavior of an austenitic stainless steel grade. So we can see that both carbon steel and austenitic stainless steel show a stable hysteretic behavior. However, there are some difference between these two hysteretic behaviors. So the main difference, perhaps, is the cyclic hardening behavior. So this cyclic hardening is the strength hardening that results from the cyclic nature of the loading. So in these figures, in addition to the hysteretic curve, I am also showing you the static stress strain behavior. Now, the difference between the cyclic and static strain, static strength, is what we call cyclic strain hardening. And we can see that for austenitic stainless steel, this is significantly larger than for carbon steel. Now, for duplex stainless steel, cyclic hardening is not as significant as for austenitic stainless steel. So now, before I explain how this strain hardening might affect the seismic performance of stainless steel, let's discuss some basic concept of seismic design. So the seismic design of a structure is based on two main parts. The first part consists of determining the internal forces in the different structural components that result from the earthquake. And the second part consists of the detailing of the structural component to ensure that they behave as intended. Now, with regard to the determination of the internal forces, there are different methods available, but they all can be broadly divided into those that consider an elastic behavior of the structure and those that account for an inelastic behavior. So the elastic analysis is the most conservative approach because in this case, it is assumed that the structure remains elastic during the earthquake. The internal forces in the structures are very large. So this approach is only applicable to situations in which the structure is subject to low or moderate intensity earthquakes, and it is only applicable to specific types of structures. Now, because the structure is designed to remain elastic, this method doesn't require any special detailing of the structural components, which means that this design approach might not be the most efficient one. Now, the good thing about this approach is that it should be possible to be extended to the design of stainless steel structures, and in fact, we expect that this is going to be the case in the next version of the seismic design code. Now, when design is based on a plastic analysis, the earthquake is assumed to be resisted through the inelastic deformation of specific structural elements. And because of this, the internal forces in the structure are assumed to be lower than those that you would get from an elastic analysis. Now, because we're assuming that the structure will deform inelastically, in order to prevent unwanted failure mechanisms and ensure that ensure a ductile behavior, the different structural elements in the structure have to be detailed so they can behave as intended. So these detailing requirements include the limiting of the width to thickness ratio of the energy dissipating elements to ensure that local buckling is not going to prevent the development of the inelastic deformations, and the member is going to reach the plastic resistance. There are also requirements related to the maximum embrace length, which are intended to prevent global buckling of the structural members. Also, the structural elements that are assumed to remain elastic have to be designed based on the maximum force the energy dissipating members can develop. So this is to ensure that under no circumstance they will behave inelastically. This issue here is very important because it implies that it is important to be able to accurately predict the resistance of the energy dissipating members. Okay, so here I'm showing you the seismic design parameters that are used in the American Design Code These parameters are very important when carrying out a seismic design that accounts for the inelastic behavior of the structure. So the first parameter is the response modification coefficient, which is given by the letter R. And this parameter is used to reduce the forces that are calculated from an elastic analysis to account for the inelastic behavior of the structure. We also have the system over strength parameter, omega sub 0, which is used to account for the additional strength beyond the design strength that the structure is able to provide before becoming a mechanism. So this parameter is used to calculate the forces of the non-dissipative elements that have to be, the forces that the non-dissipative element have to be able to resist to ensure that they remain elastic during the earthquake. The last parameter is the deformation amplification factor, which is given by C sub D. And this parameter is used to calculate the inelastic story drift of the structure that is expected during the earthquake. So is strength hardening helpful for seismic design? My answer would be yes, but only if you are able to accurately account for it. So for carbon steel, the stresses in the structural members do not depend significantly on the amount of plastic strain. And because of this, it is relatively easy to calculate the resistance of the energy dissipating members. Now, because the resistance of the energy dissipating members can be estimated relatively well, this allows for a more efficient design of the non-dissipative members, which, as I mentioned before, have to be designed based on the maximum forces the energy dissipating members can develop before they can develop when they are yielding. Now, because of the strength hardening, and more importantly, the cyclic hardening of stainless steel, the resistance of the energy dissipating members is not that easy to calculate. So there are two design options that we are considering for stainless steel. With both options, the strength hardening of the energy dissipating members has to be taken into account when designing the non-dissipative members. And this is, as I said before, this is so that you can make sure that these members are not going to yield during the earthquake. So with the first option, the energy dissipating members are designed without considering strength hardening. And because of this design option is conservative and will lead to structures with oversized dissipative members. Now, because the energy dissipating members are oversized, the non-dissipative member will also be oversized. So the advantage of this design option is that you could argue that if this design approach is followed, most of the seismic provisions for carbon steel could be applied to stainless steel. And what I mean by this is that stainless steel could adopt the same response modification coefficient and the same deformation amplification factor that is used for carbon steel. Now, the seismic, the system over strength factor, omega sub 0, would be larger for stainless steel. And that means that the values that are given for carbon steel wouldn't be applicable. Now, a more efficient design could be achieved if strength hardening is accounted for when designing the energy dissipating members. So this would be the second option. Now, the issue here is how to account for this strength hardening. How much strength hardening can be reliably achieved during an earthquake? So One way of accounting for the strength hardening might be using a design approach that is based on the continuous strength method. The issue here is that at the moment, this method has not been developed yet. So if strength hardening is accounted for when designing the energy dissipating members, it is likely that using the seismic design parameters for carbon steel will be unsafe. And because of this, it is likely that all the seismic design parameters will need to be rederived for stainless steel. Now, one way around this issue might be to perform a seismic design that is based on nonlinear response history analysis. Now, in this case, you would not need to use seismic design parameters because the effect of these parameters is already considered in the analysis. Now, it is very important that if you follow this approach, you have to use the Rambert-Osgood material model to represent the behavior of the structure. And you will also need to account for the cyclic hardening of the material. Okay, so this is my last slide. And I'm showing you here some of the research that is going to be needed to develop more comprehensive design rules for stainless steel structures. So first, one of the most important things is that we need to better understand the cyclic behavior of stainless steel. There is some research at the moment, but this is mostly on austenitic stainless steel. For duplex, it seems that the cyclic hardening behavior is more similar to carbon steel, but we need more tests on different alloys and also on different product forms to better quantify the amount of strength hardening that can be reliably used in design. It is likely that we will have to define an upper bound and also a lower bound for the strength hardening. The lower bound will be used when designing the energy dissipating members, and the upper bound will be used when designing the non-dissipative members. For duplex stainless steel, there also need to be more test evidence on the fatigue life under large strain cycles. Now, we don't expect that this is going to be an issue, but it would be useful to have test evidence that show that the fatigue behavior of duplex stainless steel is similar to the behavior of carbon steel. Now, also because the seismic design rules for stainless steel are most likely to be based on the existing rules for carbon steel, it is always useful if the research on the cyclic hardening behavior or the fatigue life of stainless steel is presented as a comparison against the behavior of a carbon steel gray. We know that the current seismic design rules work for carbon steel, and because of this, by using the behavior of carbon steel as a benchmark, it is always helpful when deciding if some of the rules can be extended to stainless steel or if they need to be modified. For duplex stainless steel, the development of pre-qualified welding procedures will also make it easier their use in seismic applications. And for welded joints between dissimilar metals, such as those between austenitic and carbon steel or duplex and carbon steel, it would be useful to have more data regarding the ductility and toughness of the welded joint. Another area that is important and that will need further research is the derivation of the seismic design parameters for different type of structures. So of particular importance here is the system over strength factor, which, as I mentioned before, it is likely that it will need to be revised irrespective of whether strength hardening is considered or not when designing the energy dissipating members. The derivation of these parameters is likely to be based on numerical simulations involving nonlinear response history analysis for different types of structures. And again, when doing this type of analysis, it is always useful to compare the behavior of a stainless steel structure against the behavior of a carbon steel structure. Another aspect that is worth of research is assessing whether the pre-qualified connections that are currently used for carbon steel moment resistant frames can also be used for stainless steel frames. So this type of research will require testing of some of the connections that have been developed for carbon steel to see if they meet the seismic, if they can meet the seismic requirements. So in this case, the stiffness requirements are the ones that require more investigation. The last research topic I got here is about looking at extending the continuous strength method to cover the seismic design of stainless steel structures. So it is possible that the CSM material model might need to be modified to account for cyclic hardening. So in this case, it would be useful if you could design a structure using the CSM and then compare the behavior against the behavior you will get from nonlinear response history analysis. Now, one thing to consider is that pushover analysis might not be able to capture the behavior of stainless steel structures under seismic loads because of the significant strain hardening. Okay, so now I will leave you with Nancy for the rest of the webinar.
Hello, everyone. Now, I'm going to take you through some research updates on the themes of composite steel concrete construction using stainless steel. So first of all, why is this important? Well, the use of stainless steel in concrete-filled hollow sections, there are a few reasons why this might be useful. Obviously, if you want good corrosion resistance, and I've shown here the Stonecutters Bridge, which was an example where duplex stainless steel was used for the upper portion of the bridge towers. Another application is for fire resistance. For example, when you want very large columns in open spaces such as airports or other large infrastructure projects, that might be an opportunity where you want to use stainless steel concrete filled structures. And composite beams, well, the main application area here would be for bridge structures, bridges which are exposed to chloride ions either by the sea or due to de-icing salts, which can be very, very corrosive. Or bridges just where you need to minimize maintenance. For example, they run over a railway bridge and it's hugely expensive to shut the bridge to carry out maintenance. So the clear reasons why we need design rules for composite construction. Have we got any rules? Well, not yet, but there has been significant research over the last 15 years around the world. What's happening in Europe? Well, at the moment, Francisco and I are writing a design guide on the design of composite beams, stainless steel and concrete. And that will be published towards the end of this year, whereupon we hope to convert it to a CEN technical specification, which is the necessary process needed before inclusion in Eurocode 4, which is the Eurocode for composite construction. In terms of the concrete filled products, there's already a CEN technical specification being written that covers high performance steels. So stainless steel and high strength steel will be included in that and ultimately it will be included in the Eurocode. In Australia, I understand, based on research carried out here in Australia, there is work towards design rules being included in the standards there. Moving to the States, we are working with AASHTO, who are the US Transportation Agency, and the NSBA, National Steel Bridge Alliance, which is part of AISC. And we are writing a collection of guide specifications on structural duplex stainless steel for bridges. So it's a family of coherent specs, materials, design, and that's the part that covers composite, and then complementary specifications covering welding, fabricating, and constructing. So around the world, there's a lot of activity in developing the design rules. So let's just have a think, well, are special design rules really needed? How will stainless steel composite beams behave differently? Well, on this slide, I'm showing you the behavior of carbon steel and duplex stainless steel. I mean, traditionally, when you're calculating the plastic resistance of a composite cross-section, you represent the stress distribution as stress blocks in the concrete and the steel. And this assumption, well, it is okay for stainless steel, but it's less well represented by these stress blocks. As you can see in the diagram, look, the strain hardening of the stainless steel, shown here in the red line, and also there's a larger portion of the steel section that is subjected to stresses lower than the yield strength. So when calculating the bending resistance of composite beams made of carbon steel, your design code will tell you, right, the plastic bending resistance you get when assuming a stress block distribution, you have to reduce it if the position of the plastic neutral axis is below a certain amount. And this is because you have to avoid premature failure due to crushing of the concrete slab. And in the Eurocodes, we call this, it's a beta reduction factor. And it reduces linearly as the position of the neutral axis moves down. Now, you've probably worked this out because of the more rounded stress strain behavior of stainless steel. You need to use a different beta factor. And we have been busy deriving appropriate beta factors simply by comparing what the actual stress strain distribution for the steel and the concrete would be and dividing it by the plastic resistance obtained assuming the stress blocks. So there's more scatter than you'd expect with carbon steel because the model is just less suitable for stainless steel. So you have to be aware that it could be very conservative, this stress block model for stainless steel, and in some cases it would be worth the extra effort of using the actual material model, for example the Ramberg Osgood material model, in your calculations. What about shear connectors? Well, yes, you can buy austenitic shear studs, austenitic stainless steel shear studs, because this form of construction is actually used and has been used for many years in the nuclear industry. So it's not something brand new. There's been a lot of experience stud welding, austenitic shear studs. Working with the University of Southampton, recently there was a program of push-out tests carried out, duplex stainless steel plate and austenitic stainless steel shear studs in comparison with carbon steel shear studs. And they showed excellent results. Austenitic stainless steel shear connectors are well able to provide the ductility required for plastic design. And you can calculate their resistance using the same equations that you currently use for carbon steel. One thing to remember is that the ultimate tensile strength of austenitic shear studs will be larger than that of carbon steel shear connectors. So possibly in the future, it may be possible to reduce the number of shear connectors to benefit from that higher strength. And as I've put on the slide, it's not a good idea to use carbon steel shear studs. It's difficult getting the ductility and the toughness of the weld that's needed. So our recommendation is to use austenitic stainless steel shear studs, which are available. Moving on to the design of slip critical bolts, which has been an area where there's been a lot of research on in the last 10 years. Well, you need slip critical bolts in the types of structures where deformation has to be limited. For example, structures like bridges, or cranes, towers of wind turbines that are subject to variable loading. And there were no rules for stainless steel, and there were lots of queries about, well, how would you avoid galling that sometimes happens with stainless steel? What's the impact of the stress relaxation characteristics? What are the slip factors for stainless steel? So what would happen is that when you had a project that needed slip critical bolts, for example, that Stonecutter's bridge tower I showed you at the beginning, then you'd have to carry out project-specific investigations. And this was done for Stonecutters, and these are the bolts here that were used. But that's not really terribly practical for most projects. So SCI worked with about 6 or 7 organizations in Europe. The work was led by the University of Duisburg-Essen in Germany, studying the performance of stainless steel slip critical bolts. There were a wide test program of bolt tightening tests studying both austenitic and duplex bolts, property class 80 and 100. So that's with a tensile strength of 800 and 1000 megapascals, and varying bolt diameters. And the study showed that it was possible to have preloaded bolted connections in stainless steel, provided the correct alloy, tightening method, and lubricant were used. We found that the pretension losses due to creep and relaxation effects were comparable to those for carbon steel. We determined slip factors on grip blasted surfaces that again were similar to carbon steel, and providing correct lubrication was used, then galling could be avoided. So the project involved a number of studies on the different parameters that influence slip resistance. So here we have when we were looking at the slip factor, and clearly that depends on the topography of the faying surfaces as well as the surface roughness, RZ. And I just showed you this slide, which is quite interesting. Both surfaces shown here have an RZ of 40 micrometers. The upper surface is shot blasted, and that was shown to have a slip factor of 0.2, and the lower grit blasted. And due to the higher asperity, sharper edges, led to better mechanical interlocking and therefore the higher slip factor. So in the end, the guidance that went into AISC 370 on slip-resistant bolts, and which is going into the second generation Eurocode, is going to be based on grip-lasted fairing surfaces. But there are tests which can be carried out if you want to determine the slip factor for other types of fairing surfaces. Yep, this is the guidance that we put in 370. So what about the pretension? Now, this recommendation is different to what you'd be accustomed to for carbon steel. The studies that were carried out showed that it wasn't possible to guarantee a fastener pretension of 70% of the ultimate tensile strength in all situations. You certainly could for the smaller bolts and if you had the hardened washers, but for the guidance that's currently given, we felt it was more appropriate to give the rather conservative guidance of the fastener pretension being limited to 70% of the yield strength of the bolt. And as more research is carried out, then we will see that value raised to 70% of the ultimate tensile strength. And the Sirocco project did lots of installation tests on slip critical bolts and demonstrated that correct installation led to excellent performance. However, because data is limited, it is necessary to carry out a bolt tightening qualification procedure for each project still. So it's not possible yet at this stage to have standard installation parameters, but work is underway looking into that. Now, in the last couple of minutes, I'm just going to give a very quick bird's eye view of other research that's underway. Firstly, I wanted to mention what SCI has done in the last 26 years. We've run 6 events drawing together researchers who are active in the field of structural stainless steel. We've shared advances. We've built a community by opening people's eyes to what's happening in different parts of the world, preventing duplication and leading to higher quality research. And we've got the people who write the design standards together. And we believe the cooperation has led to more practical, economic, and comprehensive design standards, which ultimately lead to more cost-effective structures and a greater use of the appropriate application of stainless steel in construction. So the 6th event, that was held in 2022. Rather a small number there. Quite a few joined us online because it was towards the end of COVID. The proceedings are published in the JCSR or other peer-reviewed journal. Now, there's some situations in which the type of member you're trying to design falls outside the scope of a design standard. And in these situations, design by testing is the right solution. And to minimize the number of tests needed, you complement it with numerical analysis, which helps you cover a wider range of cases. And this is the sort of work that SCI has carried out for several manufacturers wanting to design innovative structural products. And so here's an example of a stainless steel wind post. You can see a complex geometry. It's a lipped angle section, a continuous ray of perforations, complicated connections back to the block work. So SCI devised a test program and then supplemented the results with numerical analysis and developed a methodology in accordance with the Eurocode. and carried out a reliability analysis. So beyond SDI, what else is happening in the field of structural stainless steel research? Well, just a couple of slides because our time is up really, but there's a RESIST project in the UK for UK universities, all with a lot of expertise on structural stainless steel. And here they're focusing on the ductility of stainless steel, how the strategic use of highly ductile stainless steel elements in key locations can actually enhance the performance of structures under extreme loading. So that's the RESIST project. Then moving to Singapore, there's been about 8 years, I reckon, of stainless steel structural research at NTU in Singapore, and currently the sorts of topics being looked at are novel cross sections, built up members, looking at laser welded fabricated members. Now they're interesting because you have low residual stresses, so for example higher buckling curves can be used, and printed stainless steel structures. And this is just one example. There are universities around Europe looking at a number of topics of structural stainless steel. So my closing slide on research, just a few suggestions. We're still needing comprehensive design rules on stainless steel angles, which is sort of funny because when I started working in the field of stainless steel more than 30 years ago, it was with masonry support angles that I started, and yet we're still needing comprehensive rules on the behavior of slender cross-section angles and unequal-legged stainless steel angles. And there's work underway in the States, at Imperial College London, possibly elsewhere too. Stainless steel, you may remember, has a very low thermal conductivity, and so it's appropriate for some applications in energy efficient structures, and for these you sometimes have long slotted holes, so that's another area where research is needed. Of course, connections, there are quite a lot of possible research topics still needing work. Complete connection performance, connections between carbon steel, often stainless steel is bolted or welded back to carbon steel. And hollow sections, the guidance in AISC 370 on hollow sections is somewhat limited. There are certain topics such as moment connections, plate to hollow sections, and rectangular hollow section connections, which is missing. And these are all the types of connections where it's governed by deformation rather than strength. And finally on that slide, of course, life cycle analysis is an important area requiring research, and it's not an easy subject to study. It sort of requires a multi-discipline approach, but it's important that as more and more clients need to understand the sustainability impact, carbon footprint, and the full life cycle analysis of the structure. And stainless steel is good news in this topic because it has a very long life cycle with low maintenance costs, fully recyclable, high end of life recycling rate. That finishes our report and summary of research into structural stainless steel, and it finishes our webinar series. So my closing remarks are thank you for joining us. Recordings of all 4 webinars are some of them are already available and some will go up shortly, available from YouTube channels, Nickel Institute, IMOA, SCI, and also from the New Zealand Stainless Steel Development Association website. And there will be a half-day, I understand, face-to-face seminar organised by CSOC later this year.
Thank you very much, Nancy and Francisco. Dear listeners, if you have any questions concerning this presentation or about any nickel-related topic, kindly send us your question via our webpage. Once you enter www.nickelinstitute.org, you will immediately see the yellow banner Technical Help. Click on it, register, it's all free of charge, and fill in your question. One of our experts will come back to you fastest. Thank you all for attending this webinar. We are looking forward to have you on one of our next webinars again. Goodbye.